This video is to accompany section 32.2 on cMOS output stages, particularly looking at how we can drive them fast enough to avoid serious shoot-through current. Remind you what the problem is. We have got a cMOS output stage that consists of two field effect transistors, the output between them. Each one of the field effect transistors is enhancement mode, and the one that goes up to the positive power supply is a PFET, and the one that goes to ground is an NFET. So what we have is two gate voltages here. And if this gate to source voltage is high enough, we turn on the NFET. If this gate to source voltage is sufficiently negative, then we turn on the PFET. So let's take a look at what that means. Particularly, how will we avoid getting shoot-through current? There's really two approaches we can use. One is that we can arrange that neither transistor is or that we don't have both transistors on at the same time, so that one or the other of them is always off. And one way to do that is to drive them with separate control wires, so that we turn off one and wait a little bit and then turn on the other one. And that's often used for circuits like this where we really have to make sure we're avoiding shoot-through current. The other approach is to control them simultaneously, so we only have a single control wire, and then try to make sure that if we do get any shoot-through current, it doesn't last very long. So let's try that one first. This circuit, incidentally, can often be symbolized as an inverter, because if the input is high, then we're going to turn on the NFET, turn off the PFET, and the output will be low. Similarly, if the output is low, we'll turn off the NFET, turn on the PFET, and the output will be high. So this is in fact the way a cMOS inverter is made, and we'll be using pre-made cMOS inverters because that's easier than making them out of separate transistors. But we will use power transistors as separate transistors. They are very rarely packaged together in the same package. Okay, so what's going on here? If we look at what's going on with the gate voltage, let's just take a look at what happens in the gate voltage. Well, if it's down here at 0 volts, the NFET's off. And in fact, up until we get to about the threshold of the NFET, we say off. And above that, so this is the NFET, is on if we're above that voltage, off if we're below it. Let's look at what's happening with the PFET. For the PFET, we have got the, let's call this the positive, and we have the threshold P is negative with respect to that. And up here, the PFET is off because the gate to source voltage is more than the negative threshold. So this is V plus V threshold P. So the difference here is the threshold voltage. And down here, when the gate voltage gets sufficiently negative with respect to the source, the PFET is on. Okay, one thing obviously that we can do is that we can make our positive voltage small enough, PFET is off, and then when the NFET is on, and the NFET is off when the PFET is on. If we make the positive voltage small, we can make sure that we don't have both transistors on at the same time, just because for the gate voltage to be high enough to turn this one on, it'll be high enough to turn this one off. Unfortunately, that puts a pretty strong limit on what our positive voltage can be. And usually we end up having to run at higher voltages in order to get enough voltage for driving our load. For instance, if we're driving a loudspeaker and we want to get a lot of power into the loudspeaker, then we're going to need a fairly large voltage. V squared over R is if you're driving a resistive load. And so what we're often going to have to work with is this situation here where we have a forbidden region here in the middle that we actually have to go through. All right, so the way we go through that, the way we avoid it being a serious problem for us, is we go through it quickly. And that means that we have to get the gate voltage from being down here where the NFET is off and the PFET is on, very rapidly up into this region where the NFET is on and the PFET is off. The important part is between these two thresholds here, we want to be changing the gate voltage very quickly. Well, what does that take? The gate voltage is driving these two gates here, and they are, first approximation, capacitors. So if you want to drive a capacitor quickly, you just need a large current. So the way that we want to drive this thing to avoid spending much time in this forbidden region is to use a large current to drive it. And there are some simple circuits we can do for that. The simplest circuit, of course, is just whatever your device is that's producing the signal. So you have some digital logic here, perhaps a comparator. We'll get to comparators in a little bit. You might have something looks kind of like an amplifier, except for that the output of comparator is always all the way near the top rail or near the bottom rail. It's not a linear output, but a digital output, high or low. And we could just drive that into our pair of transistors. Okay, so we could drive that directly. And what we're going to be limited by is what is the current output of the comparator. If the current output of the comparator is large enough that we can drive this thing quickly enough, we're done. But a lot of times it won't be. And then what we do is run it through a digital amplifier. And the simplest sort of digital amplifier is just an inverter. So instead of running with a single wire, we run it through a digital amplifier. Now, then our question becomes is, what's the current output of the inverter? And that depends on what family of inverters we're using. In this class, we'll be looking at the 74 HC series or the 74 AC series. The 74 is just a standard logic family. They come from originally transistor logic, which nobody uses much anymore. HC is high-speed cMOS. AC is advanced cMOS. And the inverters are 0-4 in the different families. So if we're looking at a 74 HC04, 74 AC04 is the inverter, how much current do we get? And, well, that depends on, to some extent, what sort of voltage drop we're willing to have. These things don't behave like constant current sources. And in fact, the 74 HC04 and the 74 AC04 behave more like they have resistor as the output, so that if you're trying to drive a particular current there, you can look at this as what sort of resistance is this equivalent to. And then you can look at, okay, if I'm trying to drive a capacitor, the resistance here would tell me how fast I can drive it. A bigger resistor, slower RC time constant, longer it takes to drive it. And unfortunately, they don't really tell you on the data sheets what sort of resistance you get, what sort of current you get at what voltage, anything like that. But it's a pretty easy thing to measure, and I have measured it. I have that result in the textbook. And what it comes down to being is the HCO4 is about 36 ohms series resistance for both pull up and pull down. And the ACO4 is about, maybe 9.8 ohms up and about 7.5 ohms pulling down. Now that's with a 5-volt power supply. With the different power supplies, smaller power supply, these are going to be higher equivalent resistances. So this 36 ohm for the HCO4 is not very different from what most of the comparators are capable of doing. Again, you can measure the equivalent output resistance of the comparator to find out how much this is going to help. And the HCO4 is not going to help much for most comparator families. The 74ACO4, though, is a pretty low resistance. The advanced cMOS is good for driving beefier loads. And with that, you can drive these things fairly quickly. What if you need it faster, though? What if that's not enough? Depends a lot on how big these transistors are. If these transistors are very large field effect transistors, trying to drive a large current to a big motor or something, this still may not be fast enough. We may still be spending too much time in the intermediate zone. And one thing that you can do is to go one step further and to say, well, we don't have to use the same inverter for both. We can drive one for the PMOS and a different one for the NMOS. And the signals will be the same here, but each one of these amplifiers now, all of its current is going to just one of these two gates. And so it's got a smaller capacitance to drive. It'll charge it up quicker and move through the forbidden region faster. What you're going to be doing in your lab is to experiment with different ways of driving a pair of transistors. We'll take the function generated directly from the Analog Discovery 2. We'll compare it to a signal to get a comparator output. We'll also take it through one inverter or separate inverters like this and take a look at what happens to the output signal here. So looking at that with the oscilloscope, see what is the difference in how quickly we can drive this thing. We can also, if you want, take a look at currents, see how much current you have flowing through your transistors. And I think that's it for this section. And we'll look later at more detailed models of timing for field effect transistors. So not this hand wavy, it's sort of like a capacitor, and it's, you know, smaller resistor makes it faster. That's a very approximate thing. We can do things more precisely than that if we need to. And we'll also look at another application of this cMOS output stage besides just a simple inverter.